Hello, good day. So welcome to our NumPy part 5. So probably this one is the last section for our NumPy. So after this one, we will proceed to the Pandas library. So for this topic, we'll be talking about solving systems of linear equations in using the NumPy library, and also the very important concept of eigenvalues and eigenvectors. So I know you're familiar with solving systems of linear equation. So for example, so we have this sets of equation. So for example, how about we have this equation? For example, 2x minus y is equivalent to 4. Then we have 3x plus 2y is equivalent to 13. So our goal here is to find the solution for the x and the y. So for this example, we will be using deriving two variables, which is x and y. So this one is very easy if you're using the NumPy library. So let me just define this one. So actually, there are many methods in solving for x and y. You can use the substitution method. I know you're familiar with this one. You transpose the certain variables and constants to the left or to the right. You have also the elimination method. So you multiply this with a specific value and then add to derive another sets of linear equations. And what we will be using here is the matrix. We will use the augmented matrix method. So for example, I have this sets of linear equation. So let me write this in our annotate.net so that this will be much clearer because this Jupyter notebook is crowded. So let me rewrite this again. So I have written this one for the example. So let me clear this one. So this is Epic Pen. It's not part of the graphing calculator. So let me rewrite this once again. So given a specific value, again, so I'll write 2x minus y. So it's equivalent to 4. Then we have 3x. Then plus 2y is equivalent to 13. So again, we'll use the matrix method. So you can define this as a matrix. Okay, so first before how do we solve this one? So we can denote this one, let me have the blue color. So we can denote this one as ax is equivalent to b. Okay, where a, so we say this is the inverse of the matrix multiplied by a, which is this one. So this will be equivalent if we multiply both sides by the inverse of the matrix. So this will be the inverse of the matrix times b, which is this 4 and 13. Okay, so as you can see here, if you multiply the inverse by the original, so it will result to the identity matrix. So we can denote this as identity of x. So the inverse of a multiplied by b. So in simple explanation, so we can derive the solution by x is equivalent to the inverse of the matrix times this one, the b, which is 4 and 13. Okay, so what's the first step? So the first step here, so let me just adjust my screen. So the first step here is to take the specific value and went for the matrix form. So for example, if I write this in matrix form, so this will be 2 minus 1. Okay, so this will be 3. This will be 2. Then we have the x, or the variables. So this will be x, y. It's equivalent to the matrix of 4 and 13. Okay, so if you distribute this one, if you do matrix multiplication, you will arrive at these sets of values. So what will we do? So according to the formula, so we will first find the inverse of this one before we can derive the solution. So again, if you remember from the previous lecture about our inverse of a matrix formula, so let me refresh you again. So to be able to find the inverse of a matrix, okay, so a formula is 1 over the value of the determinant and the adjoint, okay, adj of A. So this is adjoint of A. So first, we will find a specific determinant. So first, let us solve for the determinant, which is denoted by this one. So again, if you remember, in solving the determinant, so let me adjust this one. So in order to solve for the determinant, okay, or this one is a 2 by 2 matrix. So what you will do is, again, is AD minus BC. Okay, so if we have this specific matrix, so let me rewrite again. So we have 2, negative 1, 3, and 2. Okay, so we have this one. So what will be the determinant of this? So the determinant of this one will be equal to 2 times 2. So minus, we got 3 times negative 1. Okay, if I'm not mistaken, this will be 4. Okay, let us adjust again. So this will be 4. So this will be plus 3 if you distribute the sign. So negative 3 times negative 1 is equivalent to 3. So our determinant is 7. So that is our first solve determinant for this one. We needed 1. Then we find the adjoint of A. So we will not use anymore the cofactor and minor method. So there's a shortcut for this one. If you have only a 2 by 2 array, so what you will do, okay, so let's solve for the adjoint of this one. So solve for example, of adjoint of A, which is this one. Okay, so what you will do is this one. You just flip this 2, which is A, B, C, D. You just flip this one. So let me write this one. So for a 2 by 2 matrix, so let me write again. So this one is A, B, C, D. Okay, so the adjoint of this one, if you shortcut this one without using the cofactor and the minors, so this one is D, this one is A, this one is B. You reverse the sign. Okay, so this one is C, then you reverse also the sign. So if you apply this one, so the adjoint of this one, let's flip 2. So there's no change, although they're both 2. So this one is 2. So this one is 2. If we swap this one, there's no change. So 2, 2. Okay. Then we flip the sign. Negative 1. So this one is 1. Then 3. So this one is negative 3. So this one is the adjoint. Okay. So then the formula, if you remember, okay, so the inverse is the product of the determinant, 1 over the determinant and the adjoint. So what we will do in order to solve for the inverse of the matrix, okay, it's just simply multiply our determinant, which has a value of which has a value of I think 7. Okay, so we got here 7. So this is the determinant, this is the adjoint. Okay, so we solve for a1. So this one, so let me write in green. So 1 over 7. Okay, so we multiply this one by this one. So 2, 1, so negative 3. And we have 2. Then, if you remember our formula, okay, so we multiply the adjoint. So this one is the inverse. Then we multiply by b. So by the way, this is the b. So this one is a. This one is x. This one is the b. So we multiplied the matrix, okay, by 4 and 13 also. So this one, so we multiply this by 4 and 13. Okay, so what will be the result? So we're solving for this one is a1 already. So this one is a1. So I go directly. Okay, so this one is the b. Okay, so we have a formula if you remember. So we're solving now for the solutions. Okay, so this is the a. Okay, so we're solving now for the solution, which is x is equivalent to the inverse of a times b. Okay, so this is the inverse, this one. So this is the determinant, this is the b. So now we solve for it. So this is equivalent to, if we multiply this one, so remember again your array, not array, matrix. So this one is a, so let me erase this one. So if you remember again the multiplication of array, so let me use red. This is a 2 by 2 matrix. Okay, so this one is a 2 by 1. So we can multiply this one, and the resulting matrix will be a 2 by 1. So this one. So our answer will be a 2 by 1 matrix. So let's multiply this one and this one first. So if we multiply that, so we will be having so 2 times 4. Okay, so let me do this at this side. So let me multiply. So this one is 1 over 7. So 1 over 7. So let's write this down. So this one is 2 times 4. Okay, so this one is 2 times 4 plus 1 times 13. Okay, so we'll have a 2 by 1. So this one is a negative 3 times 4 plus we have 2 times 13. Okay, equals 7. So let me adjust again. So what will be the result of this one? So this one is 8 plus 13. So this one is negative 12 plus, I think this one is 26. Okay, so equals 1 over 7. So 8 plus 13 is 21. So negative 12 plus 26 is 14. Okay. Then we multiply this one. So 1, 7. So we multiply. So we distribute this one. This will be, so let's distribute this one already. Oops. So let me erase this one. So if we distribute this scalar value of 1, 7 to this specific matrix, so we will have 21 over 7, and we have 14 over 7. Okay, so the solution, which is the value of x and y, will be 3 and 2. Okay, so the value of our x and y will be 3 and 2. So this will be the value of x. So this will be the value of y. So let's try to solve this using the NumPy library. So our solution here is x is equivalent to 3, then y is equivalent to 2. So let's see if we're correct. So let me adjust again. So I'll look for the specific given. So given 2, 1, 3, 2, okay. So we will define specifically. So what will be the specific solution? So let us execute this using the NumPy library. So actually this one is very easy if you're doing this on a NumPy library. So let's define the, for example, we have the A. So NP array. So I will go directly. I will not go reshaping this one. So 2, negative 1. Okay. So multidimensional already. So 3, 2. So we have the B, which is the NP array. We have 4. Then we have 13. Okay. So let's check this one. So this one is the A. Okay. So 2, 1, 3, negative 2. So 2, 1, negative 1, 3, and 2. Okay. So let's check first. So this one is 4 and 13. So this one, 4 and 13. So the way you solve this one in NumPy is very easy. You use the linear algebra solve function. Okay. So actually there's two methods. This one is the shortest one. So you use the solve. So you use np dot linear algebra, then solve. So you passed two matrices, so A and B. So the result will be 3 and 2. So that's the solution. The x will be 3 and the y will be 2. So if we check our computations, so yes. Okay, so x is 3, then y is 2. Okay. So what's the longest, not the longest, alternative? So if you follow the formula, of course, so there are other approach, but this one is a two-step approach. So if you follow the formula, it is the inverse of a matrix. Okay. Then multiplied by B, which is our constant, which is 4 and 13. So this is another approach. So let's see if we will arrive with the same value of 3 and 2. Okay, so you use the inverse. So if you remember, so np dot lin alg. So you use the inverse of the matrix. So our original matrix is A. Okay. So what will be the inverse? So let's check. So this will be the inverse of the matrix. Then we multiply this one with B. So you know that matrix multiplication, you can use dot. You can use matrix multiplication, just the same. So let's use dot here. So we have the inverse of A, then multiplied by B. So we're expecting the same result right here. Okay, so the same. So the solution is 3 and 2. Okay, so that is for a two variable for finding the solution for two variables only. So for the next one, so let me delete this one. So for the next one, how about we compute for three variables? So I think this will be same process, okay, but longer solutions because this is a three variable matrix. So again, you can use here substitution if you're familiar. You can also use elimination method, but again, we will use the matrix. So let me save this one first. So let's move on. So we'll try to solve a system of linear equation with three variables. So I already have this an example. So we have x plus 2y plus 2z equals 5. So 3x minus 2y plus z equals negative 6. 2x plus y minus z is equivalent to negative 1. So again, so we transform this into matrix. So we have a specific value here. So we have 1. So we have 2. We have 2. So 3, negative 2. You got 1 here. So 2, 1, and negative 1. Okay. So next one, we have the xyz. Okay, so xyz equivalent to 5, negative 6, and negative 1. Okay, so we have that. So again, it's expressed as a. This one is a. This is x. This one is b. Okay, so ax plus b. So again, we solve for the determinant. So I will just use this specific space here at the right side. So we use for the determinant, okay? So we solve, not used. Okay, so what will be our determinant? So our determinant will be, so if you remember this one again, okay? So 1. So we got 1. Then we have negative 2. We have 1. Okay, so we have 1 and negative 1. Okay, so minus. Okay, so plus minus, we have alternating signs. So again, so I know you know how to solve the determinant. So the next one, okay, I know you know the pattern already. So we have here 2. Then we have here 3, 1, 2, and negative 1. Okay, so next one is plus. We have 2. So this specific one. So let me erase this one. Okay, so this one. So this one. Okay, so we have plus 2. So we have 3. So negative 2. We have 2. And we have 1. Okay, so if you solve for the determinant again, so this one is AD minus BC. Okay, so same formula. So if we solve for A, so this will be 1 multiplied by, this one is 2 minus 1. So this one is 1. So minus 2. So this one is, so negative 3 minus 2. So this one is negative 5. Okay, so plus, this one is 2 multiplied by 7. So let us simplify this one. So this one is 1. So plus 10. So plus 14. So our determinant is 25. So we will use this one. Okay. So by the formula again. So we will find the inverse of this matrix. This one. This original. But we will not use again the cofactors and minors. We will just reflect specific values in the matrix. Okay, so are you ready for this one? So let me have a lot of space in here. Okay, so we'll solve for the inverse. So equals, so let me have a big matrix. Okay, so we will solve for this one. So we have this one. So we solve for 1. So again, so if you want to see this one. Okay, so we have the sign. So if you remember, so positive, negative, positive, negative, positive, negative. So let me write in green. Okay, so this one is plus. Okay, so this one is negative 2. So 1. So 1 and negative 1. Okay, so next you have a minus. So I know you know the pattern already. So if you do this one, okay, so minus 1, so you have 3. You have 1, so you have 2 and negative 1. Okay, so this is the method we will use. We will not use the cofactor in minors. Okay, so this one is let me erase this one again. So you know the pattern, but let me undo. I erase something. So let's erase this one. Okay, so we have plus, so we use this one. So then we will have 3, so negative 2. So this one is 2 and 1. Okay, well, that's a big matrix. So next one we have the 3. So this one 3. So you have this one. So this one is minus of 2. 2, we have 1 and negative 1. Okay, so next one is plus. So I will not write the black anymore. So I know you already know the pattern. So if I this one, so this one is 1, 2. So this one is 2 and 1. So it looks like 21, but this is actually 1. Okay. So minus, plus, minus. So this one is plus again. So this one is 2, 2, negative 2 and 1. So minus. So this one is 1, 2. So this one is 3 and 1. So then we have a plus. We have a plus there. So let me erase this one. We have a plus. So straight line. So this one, probably the last one. So this is 1, 2. And this one is 3 and negative 2. So let me check this one first. Then we solve again for the specific determinant here. So let me adjust our zoom level. Okay, so we solve for the specific value. So this one, if I solve this one, again, let's have a matrix right here. So this one is positive 2. So negative 2 times negative 1. Positive 2 minus 1. So this will be 1. Okay. So this will be minus. So this will be negative 3 minus 5. So this one is negative 5. So this will become positive 5 because of the negative. So this one is 1, 5. So this one is, so 3. So minus 4. Actually 3 plus 4. So this will be 7. Okay. So this one be, I'll compute this mentally now. So this one is 4. Okay. So this one is negative 5. So this one. So this one is, I think this one is 3. Okay. So this one is 3. So let me check. So 1, 1. So this one is, so 1 minus 4 is negative 3. So this one is positive 3 now. So this one is 2. So 2 minus negative 2. So this one is 6. So this one is, so 1 minus 6. So negative 5. So this will be positive 5. And the last one, so negative 2 minus 6 is, okay, so this one is 8. So positive, negative, so this one is negative 8. So is this one the adjoint? So I think this is not the adjoint. So we will find this, the adjoint of the matrix. But this time I will not use the cofactor. So let us shortcut this one. So in order to find the adjoint of this one, so this one will be the solution. So you retain the diagonal values. So we have 1, so negative 5, and we have negative 8. Okay, next one, you flip the values right here. So the 5 will be here. So the 4 will be here. So same thing, 7 and 6. So 7 will be here and 6 will be here. So the last one, 3 will be here and we will have 5. Okay, so let me erase this one. So this is already the adjoint. So again, for the formula, so let us continue. So we multiply this by the determinant and the b. Okay, so let me write this one down. So we just find here the, I think this one is the inverse of the matrix. Okay, so this one, so let me label this one. So this one is a inverse. Okay, so this one is a inverse. I think no, that's not a inverse. So this one is the adjoint. I'm sorry. So this one is the adjoint of A. So the inverse will be multiplied by the determinant, yeah. So in order to find the inverse of the matrix, so remember our formula. So to find the inverse, so we have 1 over A, so multiplied by the adjoint of A. Okay, so we have here 1 over 25. So the value of our determinant is 25, and we multiplied by this adjoint value, which is 1. Okay, so this is 1, 4. This is 1, 4, 6. So 5, negative 5, So 5, 7, 3, and we have negative 8. So we multiply this one. So let's see. So this one is, sorry about the curve. So this one is, 1 over 25. Okay. So let me rewrite that. So that one is 1 over 25. Then we have 4 over 25. And we have 6 over 25. Okay, so this one is 5 over 25. This one is positive 1/5. So this one is negative 1/5. So this one is 1/5 also. Okay, so this one is 7 over 25. So 7 over 25. Then we have 3 over 25. Then last one we have 8 over 25. Okay, so this one. So we just multiply the 1 over 25. So this is the inverse. So by the way, this is already the inverse of the matrix, but these are not the solutions. So in order to find the solution, so remember, so we have so our value of x will be the inverse multiplied by the b. Okay, so our b is, if I remember, this is 5, negative 6, and 1. So let's check first. So 5, negative 6, and negative 1. So 5, negative 6, and negative 1. So let's do that. So it's equivalent to the value of the inverse. So let's copy this one. So this one is 1 over 25. So 4 over 25. So 6 over 25. So this one is 1/5. So negative 1/5. So this one is 1/5. So let's adjust. So this one is 7 over 25. So 3 over 25. So the last one is here. Okay, so multiplied by b, which is 5. So this one negative 6 and negative 1. So if we distribute this one by matrix multiplications, so we will be having the following values. So this one is 5 over 25. So we got a plus. So this one is negative 24 over 25. So 6 times this one. So we have plus negative 6 over 25. So we're distributing. So 1/5 times 5. This one is 1. Okay. So this one is, so we have this 1/5 times negative 6. Okay, so we will have, so negative, so we got a plus 6 over 5. So 1/5, so this one is minus 1/5. Okay, so next one, so we can do this. So 7 times 5, so this one is 35 over 25. So plus, so this one is negative 18 over 25. Okay, so last one. So this one is positive 8 over 25. So if we find the value here, so I think this will be the solution. So to simplify this one, so the value of here is, so if we multiply this one, so this one is negative 30, okay? So plus 5. So this one is negative 25. So negative 25, okay? So negative 25, so let me write this one. So negative 25, so we got over 25, okay? So no problem there. So we got this one, so 6 minus 1 is 5. So 5 over 5 is 1. So 1 plus 1, okay, so let me write this one. So we got here 1 plus 1, okay. So the last one, so we got negative 10, okay. So we got 25 over 25, so the value is 1. So if we simplify this one, so we have a negative 1, so we have 2 and 1. So I think this is the solution. So this will be the x, this will be the y, and this will be the z. Okay, so let us confirm if the same result will be given by NumPy. So again, for a 3 variable, so let me have the given first. So we will be using this one. So let me zoom. Okay, so this will be our A. So 1, 2, 3, negative 2, 1, 2, 1, 1. Okay, so let's try this one. So let me just type this one. So for a 3 variable, so let's denote also as A. So np dot array. So we have 1, 2, 2. Okay, then we have 3, negative 2, and 1. Then we have 2, 1, negative 1. So we have the B. So np dot array. Okay, so we have 5, so negative 6, then negative 1. So let's execute that. So let's check the value first. So this will be our A, this will be our B. So let's find the solution. So np lin alg. So let's use the solve function. So A and B. So we're expecting here the specific value. Okay, so we are expecting the solution to be, so let me just find the result. So our solution will be negative 1, 2, and 1. Okay, so our solution will be negative 1, 2, and 1. So the same. So negative 1, 2, and 1. So that will be the solution for the system of linear equation for 3 variables. So you see, it's easy when you're using NumPy. So for the last part of the NumPy section, so we have got eigenvalues and eigenvectors. So to give you a quick overview of what is an eigenvector or eigenvalue. So these are a special set of scalars. So it is associated with a linear system of equations. Sometimes they are known as characteristic roots or characteristic values. So it has many usage on many applications. So first, they are crucial in solving systems of differential equations, analyzing population growth models, and calculating powers of matrices. So Eigenvalues have many important usage. So let me just drag something from the internet to show you. Okay, so they have many important applications, especially in computer vision and machine learning. So well-known example is the principal component analysis. So this is for dimensionality reduction or feature selection. So or you can also use the eigenfaces for face recognition. So more on that on the next electives. Okay. So in summary, so an eigenvector is a vector whose direction remains unchanged when a linear transformation is applied to it. If you look at the graph, okay, so the red arrow denotes the eigenvector. So if a transformation is applied, so look at the yellow line. So there are changes on the yellow line, but the eigenvectors do not change direction during a linear transformation or the scaling. So I will discuss only how to derive a 2 by 2 matrix eigenvectors and eigenvalues. So for this one, so 2 by 2 only. So if you want to learn 3 by 3, so maybe you consult me. But for this demonstration, I will only use a 2 by 2 matrix. Okay, and how to solve it for the eigenvectors, eigenvalues. So eigenvectors, theoretically, it has an infinite value. So as you will see later. Okay, so for example, so I got a new uh, notebook right here for writing. Okay, so for example, okay, so we have a set of matrix. Okay, matrix. So for example, we got 7, 3, 3 and negative 1. So what will be the eigen values here? And if we derive the eigen values, what are the eigenvectors? Okay, so let's do this step by step. So the definition is you have a set of a lambda, okay, of the identity matrix. Okay, so you denote this by lambda. So since this is a 2 by 2, so you remember the identity matrix is this one. So if you use a diagonal of 1, it is 0. So if you distribute the lambda, okay, so you will have a lambda of 0, then 0 of lambda. So we will solve for this one. So the next step, okay, so this is a given a set of matrix. So this one B is the lambda of the identity. Okay, so you subtract the matrix for the lambda of the identity matrix. So this one is equivalent. So our given one is, this one is 7. So 3, 3 and negative 1. So this one. Okay, so minus, okay, so we got lambda of 0, then 0 of lambda. Okay, so next, so if you subtract this one, so you will have this one. So 7 minus this one. So the next one is 3 minus 0. So this one is 3. Okay, so this one is, I think this is 3. So negative 1. So minus the lambda. I don't know if this looks like a lambda. Okay, but that's a lambda for me. So the next one is you find the determinant. Okay, so determinant of this one. So find the determinant of this one. Okay, so let's see. So we find the determinant. So 7, so lambda, so 3, So 3, so this one is -1 and lambda expressions. Okay, so equals, so let's select a different color. So let's say we'll use red. Okay, so we use red right here. So again, erase this one, then let's drag. Okay, so again, AD minus BC. So here, you remember that. So we multiply the 7. So we got lambda. So multiplied by -1 minus this one. Okay, so minus this one, determinant A times D, then minus B times C. So this one is 9. Okay, so this one, if you distribute this one, so remember your algebra. I think this is the FOIL method. Okay, so let me erase this one. So you will be having so -7, so plus the lambda, so -7, so lambda, so plus, so lambda square, so we got -9. So if we simplify this one, so this one is lambda squared. So I think this one is -7 lambda. So plus this one. So this one is 6. Okay. So minus 9. -9 minus 7 is -16. Okay. So this will be equivalent to 0. So what will be the eigenvalue? So we're solving here for the eigenvalues. So if you factor this one out, okay, if you factor this one out, so let me use a different colored pen. So this will be a lambda, so -8, if you factor this one. So lambda, so we got +2 is equivalent to 0. So now we got eigenvalues. So the eigenvalues, okay, so we got 2. So the eigenvalues, so we got +8. Okay, so this one. So let me use a blue. So the our eigenvalues are 8, and so we got 2. So we got a -2. So these are our eigenvalues. So next one, so we find their specific eigenvectors. So how to find the specific eigenvectors of this one? So you substitute the specific value to this one. Okay, so to this equation, which is this one. So 7, okay, 7 minus lambda will become 7 minus 8. Okay, and we'll go from there. So let's compute the eigenvectors of let's compute first for the eigenvectors of 8. Okay, so let's do this. Let me zoom out. Okay, so this one is number, I think this is the number 4 step. So you compute for the eigenvalues. So the 5th step is to substitute this one, okay, to this one. So you will have for example 7 minus 8. So you substitute this one. So you got 3. So you got 3. So you got a -1 minus 8. Okay. So what will be the equivalent of this one? So the equivalent of this one is -1. So 3. This one is 3 and negative 9. Okay, so from here, so we will solve, let's denote this one is as matrix B already. Okay, so the next one is we compute for the eigenvector of eigenvalue 8. So let's denote this as B. So let's say B is equivalent to negative 1. So we got 3. So 3. So negative 9. Okay. So we compute for the x and y value. Okay. So this one is equivalent to 0. Okay. So from the formula, I think this one is, I think this is B. So x is equivalent to 0. Okay. So we use here, we can use the row reduction method in order to find the specific value. So what I mean is this one. So or we can use substitution. So if you notice, this one is, if you distribute this one, so negative 1 times x. So this one is negative x. So plus 3y is equivalent to 0. Okay. So the other equation is 3x minus 9y. Okay. So 3x minus 9y is equivalent to 0. Then we will we'll assume a specific value. So most commonly they're letting 1. Okay, so what I mean, so let y is equivalent to 1, then we substitute the specific value. So we choose the simpler equation. So let y equivalent to 1. So let me use the red. So negative x plus 3 times 1 is equivalent to 0. Okay, so we solve for the value of x because we assume we let y equals 1. So if we transpose this one, so 3 is equivalent to x. Okay, so this one, so the eigenvector of value 8, the eigenvalue 8 is this one. So we got 3 and 1. Okay, so you repeat the steps for the eigenvector of eigenvalue 2. So let's denote this one by, I think, letter C. But first, let us compute first. So you use the same process for specifically for another one. So this is the eigenvalue for 8. So let me have a annotation here. So this one is the eigenvector of eigenvalue. So eigen is a German word. I think it means very specific. So of 8. Okay. So this one. So this one is the eigenvector of eigenvalue of 8. So again, as I said earlier, so we repeat the process for the negative 2. So this one. So we repeat the process right here. So we will use the same equation. So 5. So let me number this just how about letter C is equivalent to, I think, 7. Okay, so we got 7 so minus, so this one is negative 2. Then we got 3. So 3. So let me rewrite this again. Don't look like a 3. So this one is 3. So this one is negative 1. Okay. So minus. So we got negative 2. So we just repeat the process. Okay, such as mentioned above. So this one is, we denote this as C. Okay, so we got now 9. So this one is 3. So this one is 3. Then negative 1 plus 2 is 1. Okay, so we will use this one again for the eigenvalue of this one is for negative 2. Okay, so we're solving for negative 2 right here because we have two eigenvalues, so we got 8 and negative 2. Okay, so let me use green now. So we got here 9. Okay, so 9, 3. So we got 3, 1. Of course, you have the x and the y. Of course, is equivalent to 0. Okay, so both 0. So what will be the result? Okay, so again, so we use the specific equations. So this one is 9x. Okay, so plus 3y is equivalent to 0. Okay, so next one is 3x plus x plus y, I mean. So 3x plus y is equivalent to 0. So again, we assume. So let's say let y is equivalent to 1. So we use the simpler one. Okay, so let's substitute y. So let's substitute to this one. Okay, so 3x plus 1 is equivalent to 0. So what will be the, so if we transpose this one, so this one is 3x is equivalent to negative 1/3. I think 1. So 1/3 if we divide both sides by 3. Okay, so the values that we derive for the eigen value of negative 2, so the eigenvectors that we derive is negative 1/3. Okay, so negative 1/3, then we let a value of 1. So again, to make this clear, so this is the eigen, let me rewrite again. It's ugly handwriting. So this one is the eigen value of, I mean not the eigenvalue, I'm sorry. So this one is the eigenvector. Okay, of eigen value of negative 2. Okay, so this one. Okay, so negative 3 and 1. Okay, so let's check if we got the correct answers. Okay, so to sum, so we got the eigenvalues of 8 and negative 2. So for 8, we have I think 3 and 1. So for negative 2, so we have negative 1/3 and 1. So again, I'm reminding you there are infinite values for the eigenvectors. Okay, because we assume here. So if you assume let y equals 2, then that's also a legal eigenvector. So most practices they use 1, most common, but any value will do. Okay. Then to check this one also if this one is correct. Okay, for checking. So let's check for example 1. Okay, so if we check this one, so for example, okay, let's move this one. So if you check if you're correct also, so this one, so let me have the arrow. So remember our given. So we got 7, 3, 3 and negative 1. Okay, so if you multiply this with a derived eigenvector, okay, so for example 3, 1, so it's also equivalent to the product of the eigen value, okay, multiplied by the derived eigenvector. So for example, this one is 8, 3 over 1. Okay, so this one is the original, this is the eigenvector. Okay, so we're expecting here 24 and 8. Okay, so if you do this with the matrix multiplication also, so you will have 7 times 3. Okay, so 7 times 3 is 21 plus 3 times 1 is 3. So you got a 9. Okay, so this one is 9. So you got 9 minus 1. So if you can see, we have the same equivalent value. So this one is 24. This one is 24. Don't look like a 4. So this one is 24 over 8 is equivalent to 24 over 8. Okay, so this one is the same. So if you want to check for the negative 2, if we'll arrive to the same value, so you can check this one. But for 8, the eigenvalue of 8, so this proves that this is an eigenvector of that specific value. Okay, so let us check if this is correct in terms of a NumPy. So remember, it's very easy to compute in NumPy for this specific value. But this one is very different when you do this manually. Okay, so let's check this one out. So we have a specific given right here. So we will plug in the specific values for the, oops, sorry about that, I closed that one. So for the specific values, so let us have, for example, I got a matrix C. So np.array, so we plug our values. So this one is 7, 3, and we got 3 and negative 1. Okay, so let's see what is the look of this one. So 7, 3, 3, negative 1. So let us use this one. This one. So 7, 3, 3, negative 1. Okay, so let's compute for the eigen vector and value. For the NumPy, it has also the linear algebra. Okay, then you use Eigen and you pass the specific matrix. Okay, so I will explain the result. So it's computing. So the result for the NumPy eigen values, so this one, it gives 8 and negative 2. So I think we derive 8 and negative 2 for the eigenvalues. So if I'm not mistaken, it's here. Okay, so we compute for the eigenvalues, which is 8 and negative 2. So that's correct. But if you noticed, so this one is the value of the eigenvectors. So why is it in decimal places? Okay, so let me explain that. So I'll explain it to you why it's not specifically wrong. So we're expecting here 3 1. Okay, so we're expecting here 3 1 for the eigenvector of 8. Okay, so actually, so you read this one by column. Okay, so let me use this one. So the eigenvector of 8 here, so you read this one per column. So 0.94 and 31. So for the eigenvector of -2, so this is negative 0.31 and 94. So why the decimal place? And why it's not an integer? Okay. So what NumPy does to this value, it normalizes the value. Okay. So again, I will write this down. So again, I will erase this one. So what you see here, so these are normalized. Okay, so these are normalized vectors. Okay, so if you want to know how to derive this one, so this one is easy. If you're familiar with Euclidean normalization, of course you're familiar with this. Okay, you're familiar with Euclidean distance, so it's the same. Okay, but this one is somewhat different. Okay, so let's derive the specific value, y 0.94 and 31. Okay, in order to normalize this one, so we're not done yet here because I want to show you why the NumPy results in that figures. So remember, for the value of 8, okay, so we got eigenvector of 3 and 1. So for the value of 8, so let me use how about blue? Okay, so if you got 3 and 1, so you got 3 and 1. Okay, so in order to find the normalized value of this, such as the one you're seeing here, okay, so you use this specific formula. Okay, so this one is let me have the normalized. So we're deriving here the normalized form. So this one is normalized. Okay, it don't look like a normalized text, but that's normalized. Okay, so we got 3 1. So what we'll do is find the square root of the sum of squares. So this one is 3 square. Okay, so plus this one is 1 square. Oops. So this one is 1 square. This one is 3 square. Okay, so I think this is the square root of 10. So 9 plus 1. So the square root of 10, if I'm not mistaken, so let's compute this one. So what is the square root of 10? So NumPy, if you remember this one, so SQRT of 10, so that will be 3.162277. Okay, so this one is 3.1622. Okay, so 3.16 is 1 is 2.77. So let's have that kind of precision. 1 2 3 4 5 6 0 6. So 3.7. So the normalized here is the value of the vector. Okay, so 3 over, so we got the square root of 10. So I'll not write this one. So we got the square root of 10. So we got 1 and we also got the square root of 10. Okay, so these are for 8. So remember, these are for the eigenvalue of 8. The eigenvector is 3 and 1. So if you compute that, okay, so let me have this one. So let me erase this one. So let me take a note. So y different results from a manual computation. So let's take a note here. So eigen vectors in NumPy are normalized. Okay, so you apply them. So I think that's the term. Okay, so for example, so for eigen vector of eigenvalue of 8. So let's try this one. So we'll compute that one. So for this one, so we will derive this specific value in terms of a column. Okay, so let's define a specific variable. For example, so you had eigenvector of 8 is equivalent to np dot array. So again, this one is the eigenvector, okay, of 8. So let me alt enter first, so that there are a lot of lines. So this one is the eigenvector of 8 based on our manual computation, 3, 1 again. So this one. So let me, yes, 8, so 3, 1. Okay, so let me compute this one in terms of Python, the normalization. Okay, so I'll do this probably in one line. So Euclidean, let's say, value is equivalent to NumPy. Okay, so this will be the equivalent of NumPy of let's see, a square root of NumPy sum. Okay, so NumPy sum of NumPy I think square. So we square this one. Okay, this eigenvec 8. Then we sum the square. Then we provide the square root. Okay, so IEG VEC8. So you can do this. So I'm expecting the Euclidean value is 3.16. So let's see. So Euclidean val. So yes, so it's correct. So in order to find the normalized vector, so we divide this eigenvector by the Euclidean value, such as this one. We divide this one, the 3, 1, with the square root of 10. So this is the square root of 10, which is 3.16. Okay, so let's rename this one. So normalized vector is equivalent to the eigenvector of 8. So that's the name of our variable. So over our Euclidean val. Okay, so enter. So let's see. So this one is a normalized vector. So as you can see, so let me annotate. So this is what NumPy does. So it normalizes. Okay, so this one, so 0.984. So this one, then 316,227. So this one. Okay, so let's try for the other one. So I think I will just change the specific variable. So how about this one? So the eigenvalue of a -2, for example. So I think this one will be easy. Okay, so let me copy this one. So for eigenvector of eigenvalue of -2, so let's say for example we have here, so eigenvector of -2, for example. So the derived eigenvector for -2, if you remember our computations, so this is -1/3 and 1. So I will just fix this one. So this one is -1/3 and 1 for -2. Okay, so eigenvector. So let's see this one. So all right, -0.33. So that's correct. So we normalize this one. So we copy this one. Okay, so we have the same Euclidean value. Okay, so if you don't trust me, so maybe you should do this. So the eigenvector of n2. Okay, so the same. So look at this one. So Euclidean value. Wow, it's different. Okay, so we got 1.05. So in order to compute this one, so okay, the normalized vector also. So eigenvector of what's our variable name? So -2 in our Euclidean distance. Value, not distance. So enter. So we got normalized vector. Okay, so we got -0.31 and 0.94. Okay, so let's see. So -31, yes, and we got 0.94. Okay, so it's the same. So if you want to see this one, so let me zoom out. Okay, okay, maybe I will just execute this one again. So let me zoom in now. Okay, so let's compare the specific values. So as you can see here, so we have this one is for 8. So remember, this one is for -2. So this one is the normalized vector. So it's the same. Okay, so that's how you compute the eigenvalues and eigenvectors for a 2x2 array. So let me clear this one out. So we derive for the answer, but so again, it has infinite values too. So for example, I've changed the let statement here. So for example, this one. Let's see this one. So for example, I substituted, I let x equals 1. So for example, another one. So let x is equivalent to 1. So for example, I substituted x here. Okay, so this one is x. So 3 times 1 plus y is equivalent to 0. Okay, so y is equivalent to negative, I think this one is -3. So also, this is also an eigenvector. Okay, so 1 and -3. Okay, this is also an eigenvector of the eigenvalue of, I think this one is for -2. So it qualifies also. But this time, if you select the computations, okay, so if we reverse this one, so for example, so we got, okay, so another eigenvalue. So we got 1 and -3. Okay, so get a 1 and -3. Okay, so the result will be this one if you normalize this one. So let me just copy this one. So it's still legal here. So let me copy this one. Copy. So the eigenvector of 2. Okay, so let's copy. Let's see the normalized value. What will be the result? So let's copy this one. Okay, so now this it's the complete opposite. So meaning although this one, oops, I want to explain this one. So although this one is negative and this one is positive and this one is positive and this one is negative, so but your answer here is also correct. Okay, so it's possible. So again, I'm telling that eigenvectors are theoretically, it has an infinite value. So it depends on how you will substitute a specific value. So it just means, okay, so the value we derive, for example, this is the value we derive. So the value we derive here do not change direction. Okay, so it has many values, even the opposite direction or the perpendicular direction. Okay, so there's a lot value of eigenvectors. So although this one, the result of the NumPy is a different sign, but according to your manual computation, this is also a valid eigenvectors for eigenvalue of 2. So again, this will conclude our part 5 of our NumPy. So we have a lot. We already tackled a lot of topics about NumPy, but again, this is just we're scratching the surface of the NumPy library. So there's much more to learn, but I will leave it up to you to study more the other function. What I taught you are the most common ones. Okay, I hope you're enjoying our course, although this one is more on mathematics now, specifically in linear algebra. So I hope you're enjoying this one. So next time, next lecture, we will leave NumPy. So we'll go to Pandas, the Pandas Library. So again, I hope you're doing well at your other classes. My CPE third years, shout out to you. So thank you very much. See you in the next topic.